Let's have a look at the determination and treatment of errors. So there's a method known as the Kline McKlintock method of uncertainty. So essentially, if the relationship between a measured variable is known and uncertainty in a final variable can be calculated, we're able to identify what this uncertainty is. So this is the equation we're going to be looking at, and essentially it's looking at the derivative of each value within the equation multiplied by some weighting factor. Now each weighting factor multiplied by the derivative is squared. We sum all these values together and then we take the square root of it. Okay, so it's sort of a scenario where in this specific case I'm going to actually show you an example and it should become clear. So just to be aware that Wn is a weighting factor, let's have a look at this example and see how we would then apply that specific equation. So the resistance of a copper wire is given by R0 multiplied by 1 plus alpha times by t minus 20. Now alpha is a linear coefficient in this case would be for copper wire, or linear coefficient of expansion. Okay, so you're given what the equation is, you're given the over here what the nominal resistance of the copper wire is, which is 6 ohm plus minus 0.3%. You're given the alpha value, which is 0.004 per degree Celsius plus minus 1%, and you've been told the temperature, which is 30 degrees plus minus 1 degree. Now something that's quite important to look over here is that you will realize that for all the other variables we've got percentage values over there, yet for the temperature the plus minus value of 1 degree Celsius is actually the same unit as what the nominal value is. It's not in a percentage value, so keep that in mind when we look at the specific example. Alright, so what I'm going to do is I'm going to move this across to the corner of the screen over there, and then I'm going to have a look at writing all the calculations over here. Alright, so the first thing we've got to do is we've got to calculate what is the nominal resistance. So we've been told that R is equal to R0 of 1 plus alpha of t minus 20. Okay, so therefore nominal resistance can be calculated as R, which is equal to, so now R0 is 6 ohms over here, so we just look at that, we don't have to look at the 0.3% over there. So it's 6 multiplied that by 1 plus alpha is over here 0.004, so 0.004, and then we're going to multiply that by t. T's nominal value is, or the temperature's nominal value is 30 degrees, so that's 30 over there, and we minus 20. Alright, and therefore we get a nominal resistance value that's equal to 6.24 ohms. Next thing we've got to calculate is the uncertainty. Okay, and so like I mentioned, we've got to now do the derivative for each variable in this equation over here. Okay, so therefore dr over dr0 is equal to 1 plus alpha of t minus 20. Okay, now we just have to substitute values into that, so therefore that's equal to 1 plus alpha is equal to 0.004 multiplied by 30 minus 20, which is equal to 1.04. Okay, now let's look at the next variable. So we've got dr d alpha, and if we take the derivative of this equation over here, that would be equal to r0 or r0 multiplied by t minus 20. Okay, so that is equal to 6 ohms multiplied by 30 minus 20, and that will give us an answer of 60 ohms degrees Celsius. Right, and then we can look at dr dt. So that's the only variable that's still left that we have to do the derivative of. Okay, that's equal to r0 multiplied by alpha. Okay, and that would be equal to 6 ohms multiplied by 0.004, which then equals to 0.024 ohms per degree Celsius. Okay. Alright, now we've got to calculate the weighting factors. And these weighting factors is going to be looking at these values over here that we've looked at. So the first thing we've got to do is we've got to look at the nominal values, and we've got to multiply it by these percentage values. Okay, so let's have a look at the weighting factor for R0. So that is equal to, the nominal value for R0 is 6 ohms. And we're going to multiply that by 0.3%. Now 0.3%, keep in mind that percentage is a multiplication of 100. So if we've got to take away the percentage sign, we've got to divide by 100. So that will make this 0.3% equal to 0.003. And that is equal to 0.018 ohm. Right, now we're looking at the weighting factor for alpha. So again, we take the nominal value for alpha, which is in this case 0.004. And then what we're going to do is we're going to multiply it with the 1%. Again, 1%, when you take away the percentage, it becomes 0.01. Okay, and that will give us an answer of 4 times 10 to the minus 5 degrees Celsius. Finally, we need to now get the weighting factor for temperature. Okay, now weighting factor for temperature, like I mentioned, don't have percentage value indicated over here, but we're given it in the same units as what the nominal value is. Therefore, we just have to mention that. So that's equal to 1 degree Celsius. No calculation or multiplication that's needed over there. So, putting quite a bit of emphasis on that because that's a common mistake that people make. They always think, oh, they've got to now multiply 30 by 0.001 or 30 by multiplied by 1, and then they get the incorrect answer. Okay. Now that we've calculated all this and we've got all the values that we needed from this example, we're going to go back to this equation over here for the Kline McKlintock method of uncertainty. And that's what we're going to now calculate. So we're going to call WR, and that's equal to this equation here. Okay, so let's put that into perspective with the values that we've got over here. So we're going to have to say this is equal to dr0, okay, multiplied by the weighting factor of R0. Okay, we're going to square that. And then we're going to add dr, and it's going to be d alpha multiplied by the weighting factor of alpha. We're going to square that, and then dr dt multiplied by the weighting factor for the temperature. I'm going to square that, and all this is in, we're going to take the square root of that. Okay, so that is equal to dr d0, which is equal to 1.04. Okay, I'm going to multiply that by the weighting factor for R0, which is in this case 0.018. Okay, square that, plus dr d alpha. Okay, so in this case it is 60 ohms degrees Celsius. Okay, so we've got 60 over there, multiplied by the weighting factor of alpha, which is 4 times 10 to the minus 5. Square that. Plus, and then finally we're going to be looking at the temperature, so dr dt, which is 0.024, multiplied by the weighting factor for temperature, which is in this case 1. And we square that, and we take the square root of everything over here. Okay, so once we do that final calculation, we will get an answer of 0.0305 ohms, which would be our uncertainty. Alright, so once we've got this value of uncertainty, we might want to represent this in terms of some percentage value. So we can also say this has been all 0.0305 divided by the nominal value that we calculated for the resistance. Remember, that was done over here at the top of 6.24. Okay, so we divide that by the value of 6.24, and we've got to multiply it by 100 to get a percentage. So multiply it by 100, and we get a 0.49% uncertainty. Let's look at another example. So in this example, the power dissipated by a resistor is required. Okay, now again we're told over here that what the resistance value is 10 ohms plus minus 1%. We've got a voltage which is 100 volts plus minus 1%, and we've got current which is 10 amps plus minus 1%. Now, as you might be aware, there are two ways to calculate power. It's either by V squared over R, or we can have power is equal to voltage multiplied by current. So for this specific scenario, which equation should we use? Okay, so that's what we're going to be looking at. Okay, so firstly, let's have a look at what the nominal power is. Okay, so nominal power okay, so we've got the equation of P is equal to V squared over R. Okay, and if we're going to be looking at that, that would be equal to 100 squared over R, which is 10 squared, and that's going to give us a value of 1 kilowatt. If we look at the next equation of P is equal to voltage times current, okay, so power is equal to voltage times current, which is equal to, in this case, voltage is 100 volts, multiplied by current, which is 10 amps, and that's also going to give us 1 kilowatt. So our nominal power, irrespective of which equation we're using, is going to be the same. Okay. Now we've got to look at this Kline McKlintock method of uncertainty. and we're going to be looking at it for both equations. But what we're going to do is, I'm first going to be looking at this equation of power is equal to voltage squared over resistance. Okay, so let's move it up a little bit over there. So if you recall correctly, we actually need to now find the derivative of each variable correlating with the power. Okay, so therefore the first thing we're going to be doing is derivative of dP over dV, which is equal to 2V over R. If you do the derivative of that equation, you will find that it would be that. Okay, and then we also need to look at the derivative of dP over dr. Okay, and that is equal to minus V squared over R squared. It will be one of those rules you're going to have to use that's used for derivatives to get to that equation. Okay, so having a look at this, now we can determine the uncertainty. So in this case it will be WP, which is equal to so dP dV is equal to 2V over R. I'm doing this all in terms of variables. I haven't done any calculations over here to get values. So, which is also fine if we do it that way. Multiply by the weighting factor of V. Okay. And we've got to square that. Plus minus V squared over R squared, multiplied by the weighting factor of the resistance. So we've got to square all that, and then we've got to take the square root of all that. Okay. Now I'm going to leave it as an exercise for you to do, to see if you're able to calculate those weighting factors correctly and substitute the values incorrectly, which shouldn't be too difficult, but you will see that the final answer would be equal to 22.36 watts. Okay, let's have a look at the equation of power is equal to voltage times current and apply the same type of principle over here. Okay, so what we're going to be doing is we've got to look at, so I'll call this C. We've got to look at dP dV. Okay, so dP dV. Okay, so again that's equal to V. If you take the derivative of power is equal to voltage times current with respect to voltage, and you're going to also then need to do the derivative of, this is actually incorrect. This is equal to I. Okay, and then you're going to need to do the derivative of dP di, which in this case is equal to V. Okay. So now when we apply the weighting factor, or we determine the uncertainty, so we got WP as equal to, okay, so it will be I multiplied by the weighting factor of I, okay, and we've got to square that, plus V multiplied by the weighting factor of V. Okay, we square that and we take the square root of all of that. Okay, again I'm leaving it as an exercise for you to do, to get the weighting factors and then to do the substitutions correctly, and once you've done that you should be getting an answer of 14.14 watts. Okay, now if you have a look at both of these different equations, so again where power is equal to voltage squared over resistance, or power is equal to voltage times current. We've now looked at tried to determine the uncertainty for both of them. If you look at this, one we got 22.36 watts. That's for the first method that we looked at. And then we looked at, for the second one, we got an uncertainty of 14.14 watts. So obviously this 14.14 watts is smaller than this 22.36 watts. And therefore the smaller value is more in favor. Okay, so therefore, in the second method, so I'm going to put over here of P is equal to V times I is better. I wonder if you noticed the error that I made in that equation that I wrote out. And this is something that's crucial. It is just in terms of swapping terms around that can cause an error in your calculation. So if you did that calculation on your own, you would have found that you didn't get the correct answer. And so I left that error over there specifically so that you can see how difficult it, or how easy it is to make these type of errors, and which often gives you the wrong answer. So I'm just going to show you the correct solution over here quickly. Again, you can still calculate on your own, but it is at least the equation is correct. So WP is equal to dPdV multiplied by the weighting factor of V, and that's squared, plus dPdI multiplied by the weighting factor of I, that's squared, and then we take the root of that all. Okay, so the error that I made was I was multiplying dPdV with the weighting factor of I and dPdI with the weighting factor of V, which then creates errors in your calculation. So this is equal to I multiplied by the weighting factor of V squared plus V multiplied by the weighting factor of I squared, and then you get the square root of that. And now if you do the calculation on your own, which I'm still going to leave for you to do, you will then get an answer of 14.14 watts.